Hey, hello everyone. Welcome to the stream of CodeChef discussion for today. We will be discussing starters 2 and 3. So let's move to the first question. The problem says a array B of length M is said to be good if there does not exist any two different indices such that the sum of those indices is 4. Problem says, okay. So according to the problem, and we are given a array, we want to make it good, and what is the minimum number of deletions needed to make a good array? Okay, let's understand the problem. Okay, so the problem says that we are given an array consisting only of 1, 2, 3, and 4. Now, okay, only consisting of 1, 2, and 3. We need to make the array good. A good array is one in which no two elements can sum up to 4. Okay, like let's understand with test case. Here in test case 1, 2, 2, the element at index 2 is 2, index 3 is 2. And if we sum up both of them, the sum is equal to 4. Okay, so this is not a good subarray or not a good array. And if we want to make it good, we need to remove at least one element. That is, remove this 2. Now the elements are 1 and 2. Their sum is 3, which is not equal to 4. So it is a good array. So how can sum of two elements made only of 1, 2, and 3 be 4? Let's say we have chosen first element as 1. Then if we choose 2, the sum is 3. So this is not possible. This is does not lead to a bad array. Okay. And if we choose 3, the sum is 4, which does not make our array good. Similarly, if we choose 2 and 2 again, the sum is equal to 4, which makes our array bad. If we chose 2 plus 3, then it's 5, which is fine enough. It does not cause any harm. So we need to make sure that the pairs 2 comma 2 and 1 comma 3 should be absent, right? So what is the way to make sure that these pairs are absent? There can be at most one twos, and if there is one, 3 should be absent. Or if there is 3, 1 should be absent. Alright. So let's, implement this in our code. This is our final observation plus algorithm. So let's implement it in code. We have taken the vector as input. Now create a map. Iterate over the vector. Store the frequency of each element. How many at max? 2 should be present. At max 1. So, okay, okay. So what do this statement mean? The second statement mean that either 1 or 3 should be removed completely. So we want the minimum number of operation. So that's why the one with minimum frequency is removed. Okay. Now here, there can be at max 1, 2. Okay. If there are 0 twos, then no problem. Answer it as 0 operation. And if there are more than 1, 2, it should be removed. Okay. At most 1 twos. So this is it. Now let's move to the next problem. In the second problem, we are given an array as well as an integer x. X is said to be separated if there exists at least one index I such that ai is less than x and ai plus 1 is greater than x, or ai is greater than x and ai plus 1 is less than x. Okay, that is, x is said to be separated if A consists of a pair of adjacent elements with one of them being strictly less than x and other being strictly larger than x. You can freely rearrange the elements of A of however you like. Is it possible to make x not separated? Okay, so we are given a array and a number x. We need to arrange array such that no two of the neighbors, one is greater than x and other is smaller than x. That's what the question say. Here it is said that x is said to be separated if x is said to be separated if A consists of pair of adjacent elements with one of them being strictly less than x and other being strictly larger than x. Okay. So what are the possible arrangements? Note that one is strictly greater than x and other is strictly smaller than x. So if there is a x, put x in the middle and smaller number in the left, and greater number in the right. Okay, if x is present. Now, let's say the number in the smaller part is x minus 1. For these two pair of elements, one element is smaller than x, strictly smaller than x, but the second is equal to x, not greater than x. So our not separatable condition is still satisfied. Similarly, what happens if there is not a x? There can be two cases. All elements are greater or smaller than x. All right, because if all the elements are smaller than x, let's say x minus 2, x minus 1, x minus 3, any arrangement says that uh, all the pairs are smaller than x, strictly smaller than x. So this condition is automatically satisfied. In all the rest cases, the answer is no, because if x is not present and one element is greater than x and rest are smaller than x, okay, then let's say this is s, this is s, s denotes the smaller elements, and this is g, then s. So here we see that one adjacent element or one pair of adjacent elements satisfy the separation condition. So this is violated and we cannot make our array separatable, not separatable. Okay, so let's implement this. What is our algorithm? Algorithm is same as this. If x is present, then automatically answer is yes. If all the elements are smaller than or greater than x, answer is yes. In rest cases, answer is no. Okay, so is x present? In rest of the case, are smaller. This denotes that all the elements are smaller than x. Okay, let's iterate over all the elements of vector. If it is smaller than x, then there is an element that is smaller than x. So r greater is automatically false. There is an element that is greater, so r smaller is automatically false. Else condition, it matches. So x is present, so is x present becomes true. Now if any of these condition is satisfied, we can say that our array can be transformed to not separatable scenario. Okay, let's take x as input. This is it. Let's move to the next problem now. Okay, so this is Ceph and string. We are given a very large string, but actually we cannot represent the string in the given constraint. So it is given in this format. Like we are given a S, and this S is repeated k times to frame A. Okay. Let's, for example, if S is EXUN and K is equal to 3, then A becomes EXUN 3 times. That is, the strings are concatenated with each other 3 times to form A. So the length of A is n times K. So as a sign of respect for his club, Chef refuses to have I present in the string. That is, I will not be present in the string. And what happens with that I? It can be replaced with any other uppercase English letter. For example, IA is present, then this particular I can be replaced with B and the other I can be replaced with C. They can be replaced with the same character as well. So there is independence. Chef defines the score of string to be the number of adjacent characters that are equal. Okay. So the number of pairs of characters that are adjacent to each other and are equal contribute to a score. And we need to find the maximum possible score Chef's string can attain after replacing each occurrence of I with some other character. Okay, so let's understand the scenario. We are given a string made of only English uppercase alphabets, let's say A, B, C, D, and consisting of some I's. And we need to maximize the score. What is score? Score is defined as maximum number of matching adjacent pairs. Okay, so let's understand the first scenario. Case 1. I are present in middle. Let's say there is some substring in upper portion, then I, then some substring in the later portion. So what happens in this scenario? If I convert this I into the left character, that is H, what happens? We increase our score by 1 because this is one extra matching pair that we have created. What happens if we match it with the right character, that is the character present to the right of this I? Even then, the increase is of 1. Okay, so if I is present in the middle, and what is the third scenario? Third scenario is the left matching and the right matching character are same. Okay, in this scenario, if we replace it with H, the increase is of 2, and if we replace with any other character, the increase is of 0. So we would obviously want to increment or maximize the number of score. So increase is of 2. Now what happens for the boundary conditions? Let's say I is present here. Okay, some characters are present here, then I is present here. Okay, now if I replace this I, that is the starting one, with A, what happens? A, some characters, then I, then again A, some characters, then again I. This is done only two times just to visualize. So we see that okay, just replace, just keep one I in the boundaries for understanding. So how is our string transformed? It is transformed to this particular string by replacing I and concatenating with the same string once. This was the initial string. Replace with I with A. Okay. Then this I is replaced with A, and another string of same type is concatenated again. Now, what is the increase in score? This A matches with this A, increases 1. This A matches with this A, increases 1. Similarly, if we had removed it with or replaced it with B, the increase was equal to, okay, so here is an increase and here is an increase. So increase is actually 2. Here increases only of 1 because only this B matches with this B. Okay. So what is good in this scenario? Replace this particular I with the first non-matching I character. Okay. For only one I at boundary, replace it with first nearest non-matching character. Okay. Now what about there are two i's at the boundary which we stated initially. Like let's say there was an I again. Let's see. First replace with A. Then replace both the i's with A. Okay. So here is an increase. Here is an increase. Here is an increase. That is it. 3 increase. 1 increment because this last I and this first I matches. Okay. And 1 increment because this I matches with starting character. So already which gives us this case which we discussed earlier, and 2 increment is due to this particular case, and 1 increment is because this I and this I matches. This particular I and this I matches. Okay. What if we replace with B? This transforms to B, then some ABs, then BB, then A, B, and again a. So here 1 increase, 2 increase, and 3 increase. Okay, the condition is same. Similarly, what if we replaced first I with A and second with B? Let's understand this scenario as well. This one with B, then again with A, then again a B. Let's see what happened. There is an increment of 1 here. There's an increment of 1 here. There's an increment of 1 here. And there is an increment of 1 here. So how many increments? 4 increments. Okay. So what did we observe from here? If we had replaced with just one matching character, that is A, these two had matched and these two had matched. So total increment was 1. If we replaced with B, then increment was 3 again. Here also 3. Now if we had replaced the starting character with the first non-matching character and the ending character with first non-matching character, the increment is maximized. So this is what our algorithm should be. Okay. So our algorithm says us to replace starting i's with first non-matching and ending i's with last non-matching. All right. Okay. So let's implement it through algorithm. What are we asked? We are asked that what is the maximum possible score? What is the maximum possible score for this uh, given string? Hello. Sorry for delays. So what should be our algorithm now? Replace starting i's with first non-matching. Okay, so this is our first first step. Now for middle elements, replace with any of the neighbor. We analyzed it here that replacing it with any neighbor is of same scenario. And for the rest elements, what if the first starting non-matching character and the ending non-matching character are same? So in that case, for example, this one, like there is a I, this case, there is a I, then a, then again a, then a I. So here we replace with a. Now here instead of four increments, what are the number of increment? One, two, three, four, and one extra here. Okay, so there is an extra score increment because of this particular condition. So this is a edge case which we should keep in mind. That is, if starting first and last non-matching character are same, then increment answer by 1 for each concatenation. So let's move to implementation part. First condition, what if our string consists only of i's, then there is no first matching and last matching condition. So handle it separately. We need to take n and k as input, then a string of size n. Now iterate over all the string. If I find a character that is not equal to I, then we are good enough to proceed with our algorithm. And if we did not find any of them, then just output n into k minus 1. Why this? Because every character is matching and each pair matches with its each character matches with its previous element. Like if there are only a, the answer is 3, because how many pairs can be made? 3 pairs, that is n minus 1, total size minus 1, which is what we have printed. Total size is n into k and minus 1, because n one less pair can be made. Okay, so find the first and last matching indices, non-matching indices. If we did not find I, this is I1. Now iterate from backward. This is just same condition, but with I2. So we have got first and last non-matching characters. What did our algorithm say? Make all the characters same up till I1. Similarly for the last characters. Now for the middle characters, make them okay. So we can calculate answer as well together. What if the last character matches with current? Our score increases by 1, or other case, the current string is I. So we can replace it with the previous string, and our score increases by 1. That is it. If st at I1 equals st at I2, that is the first non-matching and second non-matching are same. Our answer increases by 1 for each concatenation. Okay. How many concatenations are there? K concatenations. And -1 because the first, how many number of matchings will be there? If we are writing our string 2 times, so there is 1 time that this AA appears. Similarly, if we write K times, K -1 times, these AA will appear. So -1 for that case. And what about the else part? Answer is just K times. Let's move to the next question now. Okay, so mean difference. We are given an array B, which is of length M. We define the following. Average of array is sum divided by its size and the floor of it. Similarly, maximum difference between an element B and average is defined as uh, absolute maximum of absolute values of Bi minus average of B. That is, pick up each element, take the difference with average, take a absolute, and for all such values we have obtained, the maximum value is denoted by FP. All right. So we need to compute the maximum value of Fs across all non-empty subsequences of A. Okay. FP is the maximum of all such differences, and for all the subsequences, the maximum Fs we can get is to be computed. If we did not understand the question, let's understand with an example. Like, let's say we are given this array. Now pick up any subsequence, like pick up 1, 5, 8. Okay. And for this subsequence, what is the maximum FB or FX? FX is take the average. What is average? First of all, calculate average. It's 13 by 3, which is equal to 4. Okay, sorry, 14 by 3, which is equal to 4. And now Fx is max of all these values. What are the values? 4 minus 1, 5 minus 4, and 8 minus 4. What are the values? Max of 3, 1 and 4, which is equal to 4. Okay. Now, for all the subsequences that can be generated, what is the maximum subsequence that can be generated? Like 8 is in itself a subsequence, 5 is in itself a subsequence, 8, 5 is a subsequence. So for all the subsequences that can be generated, the maximum value of fx is to be calculated. All right. So what is the first intuition that came into my mind while solving this question? If we take a small, the smallest number, and some very large numbers, this gives our answer as maximum. Because, like, let's say we have taken 2 and 100, 100, 100. We had the option of taking 3, 4 as well. Okay. But what happens if we take 3 and 4? If we take 200, 100, 100. Okay. Average increases. Average goes close to the larger numbers, that is towards 100. And since the smaller number is 2, the difference increases. Let's say if we had taken 3, if we had taken 3, average decrease, and absolute value of average, or let's say average is automatically larger than the smallest number, average minus 2, what happens with that if average decrease? This also decrease. Okay, so it's wise to ignore 3. And uh, in another scenario, what if we had taken 3 and hundreds? So is this condition better, or is this condition better, that is 2 and 3 hundreds, or is this condition better where we are choosing 3 and 3 hundreds? Okay, let's see this. Our average increases because we are choosing 3 instead of 2. And value. Okay, so what is our score in these both case where we are choosing smaller number to take absolute with? Score is average minus value to be maximized. Okay, our average increases and value increases as well. So by what factor average increase and by what factor value increase? If we say that we are having, let's say, let's understand with visualization. Okay, let's say there is a 3 here, and there is a rope which is being pulled, and the center of this rope is termed as average. All right, this particular center is termed as average. Now there is a single 100 here which is pulling this rope as well. So this 103 do not represent the weight or let's say pulling power. So our average ends up near 100, the middle of 103, which is 103 by 2, which is 51 or 52, let's say 51.5. Okay. What happens if one more person comes at 100? Okay. One more person starts pulling this particular row. Then average shifts towards this 100. All right. Where is the average now? Average is somewhere here, which is equal to 67.66. All right. So now if we increment 3 to one more value, let's say 4, or let's say we increase it by one value, 4. What happens to our average? Our average increases by a factor of 1 by 3. All right. Because 4 is increased and 4 has only one contribution, while 100 has two contributions. So average increases change from 3. So, initially we had 2 and 3. So let's say initially it was 2. Change from 2 to 3 increases average by a factor of 1 by how many numbers are there? 1, 2, 3. And initially we had 300s. So there is one more 100 pulling the rope here. All right. So change in or increase in average is of factor 1 by 4. So this particular part increases by 1 by 4. Okay. What about the value? But the value increases factor of 1. Okay. So what do we conclude? The rate of increase of value is greater than rate of increase of average. All right. So the score decreases with a choice of 3 instead of 2. Our score decreases. So that's why we conclude that choosing the smallest or the largest number is best. All right. If we have arrived at the conclusion that one of the element is first number, then iterate over all the numbers and choose all numbers from, let's say, x to end, and check the score. If this is the maximum score, update it, or uh, keep moving leftward and checking the score. All right. Let's say we had this particular string. So we chose 2, then choose 100 and compute the score, then these 200s and compute the score, then these 300s and compute the score, then these 300 and a 4 and compute the score. Like if we come to know that this score is smaller, then give up on like score calculating the score. Similarly, if we had chosen 100, then take this 2, then this 2 and 3, then this 2, 3, 4, and compute the score. All of by taking the values of all these conditions, the maximum value is our answer. So that is our algorithm. What is our algorithm? Choose the first or the last or the smallest and the largest number of our array, iterate from the opposite end. If we chose starting number, then iterate from backward and calculates to score and vice versa. So let's move on to implementation part. So let's move to the implementation part. So we are given a array and list of numbers. First, we chose smallest number. Compute the answer and compute the maximum possible answer. What is the current sum? Current sum is 0 because we have not chosen any number. Now iterate from backward. Okay, we have not sorted the number yet. Now, what is the answer considering subarray from I to n and the first number? It is equal to absolute value of first number minus the average. What is the average? The suffix sum plus the first number divided by the size. Size is n minus I plus 1. N minus I for the suffix and 1 extra for vex 0. Now choosing greatest number. Sum is 0 again. And what is the size in this? In this case, if I get a n minus 1 ends here, size is I plus 2. At the end, output the maximum answer we got. And this is accepted. Let's move to the last problem for today. Maximum product walk. In this problem, we are given a tree and we are told to calculate the maximum score according to the following scenario. We need to create a walk in a tree that is a sequence of vertices such that there exists an edge between xi and xi plus 1. The length of such a walk is said to be k. Note in particular, it is allowed for vertices to repeat in the walk. Okay, so we can start at any particular node, move to any portions of the tree, and come back to that node, or let's say end it anywhere. Okay, the score of walk is defined as follows. Start with p equals 1. Actually, it's not necessary that we start with p equals to 1, which is stated. Okay, stated here. The walk can start and end at any vertex. It confused me as well during the contest. But start with any particular node. Then for each indices, move to the node given if the value of node w is a at xi at that node. If the value at that node is positive, multiply our p with 2 to the power w. If our value is smaller than 0, that is negative, multiply it with negative of 2 to the power minus w. What do this mean? Okay, let's understand the question. Let's say we were given a tree. There are some, okay, sorry, there are some edges. Okay, we can start at any particular node. We can start at any node, then move. Okay, we need a highlighter. We can start at any particular node, let's say here, move to any of the neighbor nodes, then come back to that node and move to next node as well. That is, any particular path that can be taken is defined as a walk. All right. Now, what is the algorithm stated in our question stating? Every particular node is assigned a particular value. Let's say this is assigned 3. This is assigned minus 2. And this is assigned 1. Now, if we move to that node for the first time, let's say we move to 1 for the first time. Since its value is positive, 3 is positive. So, multiply p with 2 to the power 3. Okay. Now, let's say we move to node 2. Its value is minus 2, which is negative. Multiply it with minus of 2 to the power minus of w, and w is minus 2. So minus minus cancel. So 2 to the power 2. Multiply it with minus 4. All right. And let's say we move to 1 now. Then we multiply the answer with 2 to the power 1 again. Okay. Because of this. So our total answer now becomes 2 to the power 3 multiplied by minus of 2 to the power 2 multiplied by 2 to the power 1. All right. So it is equal to, So it is equal to 2 to the power 6 minus of 2 to the power 6. So this is the score for given path we chose, and we need to maximize this score. Since our score is negative, we could have just not chosen this particular node and moved to this node and this node. Then our answer would have been 2 to the power 4, which is the maximum possible. So what is the intuition that comes to your mind reading this question? Intuition is we need to be aware of negative score, because zero score is always better than negative scores. Okay, so how can we make sure that our score is positive? Score is positive if there are even negative nodes in our path. Okay, let's understand something else now. Is the order of path important? Answer is no. Why? Because if we had chosen the first node as I1, then second as I2, according to the properties of power, if the base are same, then powers can add upon. Okay, so this can be said as I1 plus I2. Now write I1 before or write I2 before, it does not matter. All right, so our final answer would be equal to 2 to the power sum of weight of all the nodes visited. And of course, we would like to visit even number of negative nodes so that our score is positive. So no need of considering sign in that case. Now, what are the two cases that comes to your mind? First case is there already is there already are even negatives. Pick all of them. All right. Why pick all of them? Because this increases our score, which is for sure positive. What if there are odd negatives? We need to get rid of at least remove at least one negative node. So what how to get rid of one node? The whole subtree, like the subtree can be any given subtree, like we will understand it later, but the whole subtree of that node must not cannot be visited now. So what do this particular sentence mean? That whole subtree of that node cannot be visited. So if this was our, let's understand this. Let's say we had one negative node, the second node here. What if it had two more nodes as its children? All right. If these two nodes were the children as well, and it consisted of positive numbers, let's say 4 and let's say 5, what could we have had chosen? We could have chosen we should get rid of this particular node at first in our walk. So what are the possible walks? We can either take this particular subtree, okay, or let's say a part of tree that is connected, or this particular part, or this particular part, because in all the rest parts, this minus 2 is included, and we need to get rid of this minus 2. All right. So this is what we conclude, and what we meant by the whole subtree cannot be visited, and we need to get rid of one negative node. All right. So we need to find the connected component with maximum sum excluding at least or equal to one negative node. All right. And that is our answer. So the rest thing is about implementation, how to implement it. So let's move to the code part. We need to create a adjacency list. Let's name it as graph. Okay, let's keep it global. Now create a vector to store the score or value of each node, and a extra vector denoting the subtree size or subtree sum of each node. All right. Now input the values. This assign variable changes the size and assigns the value to all the indices. Now assign the subtree sum as 0 initially for each node. Now count the number of negative nodes. Let's keep the sum of all the nodes global because we will need it later on. Okay, iterate over all the values. If the value is negative, increment the count and add the value to the sum. Now take the graph as input, or let's say adjacency list as the input. There are a total of n minus 1 edges given in the form of u comma v. Okay, now our graph is created. The first condition, that is the count of negative nodes, is even. The answer is just simple. This bin-pow is binary exponentiation. It is used to calculate a to the power b mod m. The mod is defined here, or maybe I would be needing my template for this scenario. For all right, and we were up till this part. All right. What in the other scenario? Other scenario, we need to remove one subtree at least. Okay, from the sum. Let's say the subtree is given to us as cur. Let's calculate this cur value now. Like if we, in this scenario, if we had chosen this subtree, then we need to delete this particular part. All right, this whole part. Similarly, if we choose this part, these two nodes, then we need to remove this subtree. So we need to calculate which subtree to remove to get the best answer. We will calculate it using DFS. Let's understand it. Create a DFS. Assign the subtree now. Now the minimum, we want the minimum amount of value to be deleted. So we calculate it using MI, let's say, and we calculate the maximum child. Okay, why maximum child? Let's say we are removing this subtree, that is keeping this thing. All right. If we want to keep this particular part, then this whole subtree is to be removed. Okay. What if we want to keep this particular part? So this whole part need to be removed. Okay. So this, what this denotes? This denotes the child with maximum value. All right. Edge case would be this particular node is itself a child of 2. All right. So keep that in mind as well while implementation. So max child is 0 now. Iterate over all the neighbors. Now if neighbor equals to parent, continue. For the rest part, calculate the minimum answer we could get from this particular child. Now update the subtree size of node. Now what about the minimum thing? Minimum thing is the minimum up till now, or maybe we could remove a subtree in the child part, one of the child part. So what did we get in the child part? It is denoted by temp. Now about the max child. Max child is the child with maximum subtree size. Alright. Now, if the current node is negative node is where we are applying the operations. Alright. In this condition, one more thing, which was a edge case, that is its parent's child, that is the edge leading to its parent ancestor part. That part is a subtree as well. If we consider this as a node root, then it is equal to max of max child and the ancestor part. Alright. Rest part is to be removed. Now what is mi? Mi is minimum of mi comma subtree of node, that is remove this whole part. Alright. Now what about keeping one of the child itself? For that, what is to be removed? Sum minus that child itself. So that child will remain. Now return mi, and we have already removed the minimum part here. So run the code. Okay, we wrote min child somewhere by mistake. Sum was not declared. Let's declare sum globally. Okay. Okay, val don't think was used anywhere. And here we are taking max. Alright, there is some problem. Let's go through the code again. Taking graph vector, then subtree is fine, max child is 0 initially. Okay, seems fine, but the output is wrong, so there is edge case somewhere, I guess. Let's go through the code again. Okay, maybe we are using something that we have not changed in the test cases part. Vec is changed, subtree is changed, count is alright, sum is changed. Okay, so this was the actual code. So okay, This was our max side. All right. This should work. All right. This is it for today. All the best for next contests.